Hello everybody and welcome to another physics calculus video. Today I'm going to be solving a conservation of energy problem for you guys. So let's get right to it. Okay, so this problem is adapted from chapter 7, problem 63 in the university physics textbook. And it says a cube of ice with mass 0.200 kilograms is placed against a massless horizontal spring on a table that stands 1.40 meters above the ground. The spring, with spring constant 2,000 newtons per meter, is initially compressed 0.024 meters. As soon as the spring is released, the ice block travels across the table and hits the floor. Assuming friction is negligible, what is its speed when it reaches the ground? Alright, so let's draw a picture here. So we have our ground and we have our tabletop, which is at a height of 1.40 meters. And then we have our spring on the tabletop and our cube of ice. And so when the spring is released, it travels across the tabletop and goes and hits the floor. And it has a mass of 0.200 kilograms. Alright, so what are we looking for? Well, we're looking for its speed when it reaches the ground. So if it goes and it travels along the edge of the tabletop and then it leaves the tabletop and travels to the floor, well, it's going to have the final velocity that has at the edge of the tabletop. It's going to have that horizontal component of velocity when it reaches the ground, and it's also going to have the vertical component of its velocity when it reaches the ground, because gravity is going to pull it down and give it an acceleration. So we're looking to find both of those variables and then use that to find the final velocity. Okay, so let's start off with the x direction. So this is my positive x direction and this is my positive y direction. So let's define our variables here. We have the mass of the ice cube, which is 0.200 kilograms. We have h, the height of the tabletop, which is 1.40 meters. We have gravity, which is negative 9.80 meters per second squared. I'm sorry, h should be negative as well, because it's traveling in the negative y direction. And we have our spring constant K, which is 2,000 newtons per meter. And we have X, which is 0.024 meters, which is the distance that the spring is compressed initially. We also have Vi equals 0 because initially the ice cube is at rest. And let's see, we also have our final velocity, which is what we're looking for. And again, to do that we need the horizontal and vertical components of its velocity when it reaches the ground. Okay, so we can find the horizontal component of the final velocity by looking at this point right here on the tabletop, because once it leaves the tabletop, it's going to have that horizontal initial velocity when it reaches the ground, right? Because we've learned in projectile motion that the x and y motions are independent, and so the x component of the velocity is not going to change. So we can find it right here, and to do that, we can use our handy conservation of energy equation. Excuse me. We can use our conservation of energy equation, which is the potential energy at the beginning, PEI, plus the kinetic energy at the beginning, KEI, equals all the energy at the end, so equals PE F plus KEF. Alright, now applying this to this motion from where it initially starts to the end of the tabletop, we know that the initial potential energy is the energy of the spring because that's what's storing all the energy initially. And KEI is 0 because this ice cube initially has no velocity. So we have 1/2 kx squared, which is our potential energy equation for the spring, plus 0 equals, well, there's no final potential energy in the x direction because it's all been translated into kinetic energy. So we have 0 again, plus 1/2 VFX, because it's on the tabletop, which is horizontal, squared. I'm sorry, 1/2 m VFX squared. Alright, so we know everything here except for the final velocity in the x direction, so we could find that. So solving for VF, we have kx squared over m. We have the square root of kx squared over m equals VFX, right? Because all I did is rearrange to solve for VFX. So we know that this is going to give us our correct units because K is in kilograms per second squared. X is in meters, so x squared is meters squared, and mass is in kilograms. So the kilograms cancel, and we get meters squared per second squared, and then the square root takes care of that, so we have meters per second for final velocity in the x direction. So let's plug in some numbers here. So we have the square root of K, which is 2,000 newtons per meter. And I should mention that I said that this K was in kilograms per second squared, but really newtons per meter and kilograms per second squared are the same unit. You can express the same unit expressed in two different ways, so this is perfectly valid. So 2,000 times x, the compression distance of the spring, which is 0.024, and then all divided by the mass of the block, which is 0.200. So let me just calculate this real quick. So I got 2.40 meters per second. So that's how fast it's going when it leaves the tabletop. So now we know the x component of the velocity, but we still need the y component of the velocity because we need to combine them to get the final answer. So we can find the final velocity in the y direction a couple different ways. We could use our kinematics equations, which would be totally valid. That would totally work. But in this case, it would be easier to use energy conservation again. So we know that the instant before the ice cube hits the floor, all of the potential energy that it has up here in the y direction has to be converted to kinetic energy. So it's going to have no potential energy, but it's going to have all of that potential energy is going to be kinetic energy. So we can say that the potential energy up here, which is mgh, mgh equals 1/2 m VFY squared. So let's rearrange this out for VFY. Mass cancels, and multiplying by 2 and taking the square root of everything, we have VFY equals the square root of 2GH. And again, we see that this is going to give us meters per second because H is in meters and G is in meters per second squared. So we have meters squared per second squared. And 2 is just a constant, so taking the square root of that, we have meters per second. So that's good. That's exactly what we want. So let's plug in the numbers here. We know that G equals negative 9.80 meters per second squared, and H is negative 1.40 meters. So we have the square root of 2 times negative 9.80 times negative 1.40. Alright, let's just calculate this real quick. So I got about 5.238 meters per second. So this is our final velocity for the y direction, but we want the final velocity in general. So because these velocities are along different axes, we need to use our vector addition method. So VF, the thing we're looking for, equals the square root of VFX squared plus VFY squared, right? Because using the Pythagorean theorem, these two, at this point, this is VFY and this is VFX. So we need to add these two, and so we need vector addition. So plugging in our numbers here, we have the square root of 2.40 squared plus 5.238 squared. And calculating this, we have approximately 5.7617 meters per second. And converting this to three significant figures, we have 5.76 meters per second for VF. So this right here is our answer. Alright, thank you guys for joining me today. Please like, share, and subscribe if you did like the content. If you didn't, thank you for watching anyway. And yeah, leave a comment down below if you think I made a mistake or if you have any questions, and I'll try to get back to you. Thank you all. See you next week.